Good morning, everyone. So if there's any problem hearing, I hope somebody will let me know from the online. So, fantastic. Yeah, it's just so quiet in the classroom. Everybody online, you're not hearing much, and it's because everybody in the classroom's quiet. It's not the normal buzz when we walk into a room and we all hang out and chat. But we're doing what we can, right? So we're still up in the clouds today and part of tomorrow, and then we'll come back down to Earth no later than Monday, and it could be halfway through Friday's lecture. So we're doing the more abstract foundations of linear algebra. If you've studied foreign languages, we're in the vocabulary stage again, which is the only thing maybe worse than conjugating verbs, right, when you're doing a new language. So this part is painful, but once you have the vocabulary, then you can carry on conversations with colleagues and with people you're working on, with projects, with very precise concepts, and they're very compact, okay? It just really makes the information transfer much more reliable. But acquiring that fluency takes practice and time. So just a quick review of the abstract concepts we've developed on Monday. So just our subset notation, and we allow V equals W, okay? So that does not mean that V is strictly smaller than W. V can equal W. Then we take a subset in Rn, we call it a subspace when if we take all possible linear combinations of elements in V, they always stay in V. So we say it's closed under linear combinations. And if you want to check that by doing sums of vectors and scalar times vector multiplication independently, that's sometimes easier on given problems, or you can go all the way through and just do a general linear combination, show that it works. Now, outside of this, nobody calls it the smell test, okay, but it's just a mnemonic to help you remember. If you want to check something's a subspace, if the zero vector is not in it, then the answer is no, okay? So it's just this little simple, quick thing to always have in the back of your mind. We're always trying to relate the abstract parts of linear algebra back to the down to earth, and the closest we're getting this week is really by looking at matrices. And if you have a matrix that's n by m, n rows, m columns, it naturally generates two subspaces. One subspace is the set of all vectors in the domain. If you view A as a function, if you view it as a function that maps points in Rm to points in Rn, okay, it's a function. It's all points in the domain that get mapped into zero. So that's null as in zero. It's the zero space, but it's called the null space. And why over in zero space, I have no idea, but that's what it's called. And the other one is called the range or range space, where you look at everything you can hit in the codomain as you vary x over all possible points in the domain. So if A is the zero matrix, then you don't hit very much in the codomain. You just hit the zero vector. And we'll see if A is square, for example, and its columns are linearly independent, you'll hit everything in Rn. We'll start making some connections like that and understanding what these sets look like. Okay. Another way they relate to linear equations is Ax equals B has a solution if and only if B is in the range of A. Why is that? This equation means if something is in the range, there is an x such that Ax is equal to it. So it's really the definition of a solution. So AX equals B has a solution if and only if B is in the range of A. We'll tie that back to something else we know about solutions. AX equals B if and only if B is a linear combination of the columns of A. So somehow, that's what this object must be. It has to be, but you don't see it immediately, perhaps, from this abstract formulation. And then AX equals B has a unique solution. Okay, if it has a solution, it is unique if and only if the null space of A is as small as possible. It's the zero vector in the domain in Rm. And that's because if anything that A multiplies and you get 0, then I can just add it to any other solution and it's not going to change this equation because A times that vector is 0. Okay, so, a final thing, this is kind of cute. We kind of stopped it here showing that these were subspaces, but we have a condition when A is a square matrix. We noted AX equals B has a solution for all choices of B if and only if the determinant of A was non-zero. Remember that? Okay, well, if the range of A is all of Rn, what does that mean? That means I take any vector B in here, there's always some x such that AX is equal to B. So it's just the definition, it's almost a one-liner, it's just the definition, but this works for non-square matrices. AX equals B has a solution for all possible right-hand sides if and only if the range of the matrix is all of Rn. So, once again, just trying a little bit to help build up your appreciation for these concepts and how they relate to solutions of linear equations. Anybody like to follow up with any of those comments before we embark on today's adventure? Nothing, all good from, okay, one, that's nice. Okay, so I want to make a first observation. About subspaces. If V is a subspace, then V can have one element or an infinite number of elements. It cannot simply have 2, 3, etc. elements. Okay, once we see why this is true, it'll be like almost trivial, but that's the way everything is once you understand it. But the reason we're talking about this, remember this kind of mystery once again on day 1 of class. The first chapter, we're solving equations, 2 unknowns, etc. And we kept finding that we can have either a unique solution, no solution, or an infinite number of solutions. It's not possible to have only 3 solutions to a set of linear equations. It's just not possible. And it's all tied to this notion of a subspace, okay? So why in a subspace can you not have a subspace that has 2 elements in it? Okay, so the 0 vector is always in V. right? That's the smell test. So suppose V has at least 2 elements. Okay? 0 is always there, and it may be the only vector that's in it, because 0 is a subspace. 0 can be a subspace, no problem there. So if it has at least 2 elements, well, okay. Then one of them has to be not the 0 vector. Semicolon, let's call that vector V. V not equal to 0. Now V is closed under linear combinations. Squeeze it in. Close enough. Combinations. Hence, for all scalars in the reals, alpha times V is an element of V. Okay, so that gives us an infinite number of vectors in V immediately, because there's an infinite number of real numbers, we have an infinite number of vectors now. Because V is not the 0 vector, okay? So that implies infinite number of vectors in V. And our hypothesis was only that it's not the trivial subspace consisting of only the 0 vector. Okay, so this is the root of systems of linear equations can never have 2 solutions only or only 3 solutions. Either have no solutions, 1 solution, or an infinite number of solutions, and it's due to the subspace property. Okay, so that's just a piece of philosophy. Let's do some examples with these null spaces and range spaces. So, example. Find the null space of, and we'll first do A1. It'll be 1, 0, 0, minus 1, 0, 1. Why? I don't know. It's got numbers that I can handle at 10 o'clock in the morning. Hopefully you can handle them too. Okay, so how do you go about doing that? Okay, so the null space is the x's where we get a1x equals 0. Okay? So that's if 1, 0, 0, minus 1, 0, 1 times x1, x2, x3 is equal to 0, 0. Excuse me, it has 2 rows, so it's 2 zeros there. Okay, we're good with that. So A is 2 by 3. The domain is dimension 3. The codomain is dimension 2. Okay, so let's just kind of continue our if and only if. let's just multiply this out. So we take the first row times that column, and we get just simply x1. And then we take second row, we get minus 1 times x2 plus x3, right? So we get minus x2 plus x3. That's 0, 0. Okay, let's just make a little note on the side for us. That's if and only if x1 is 0 and x2 equals x3. Okay, so those are simple equations. I'm going to write this, though, in a more compelling way. I'm going to write it as x has to look like then 0, alpha, alpha, where alpha's in the reals. Okay, see where that's going? Maybe not. So then the null space of A, so that's the set of all points, A1, excuse me, is then equal to set of all vectors that look like this, alpha times 0, 1, 1, such that alpha is in the reals. Okay, so I've written the null space as a set of linear combinations, and I chose one vector that's lying there in the null space. That's what I was able to do. Okay, so keep that form in the back of our minds as we go forward, okay? So I've written the null space as a set of linear combinations of vectors. This is only one vector, so there's not very many linear combinations, except I'm changing the coefficient, okay? But this is still a linear, all the possible linear combinations of the vector 0, 1, 1. Now, I will remark, 0, 1, 1 is not unique. I need x2 equals x3, so I could have put square root of 7 and square root of 7 in the spot, and it's the same vector. Okay, I can factor anything in and out, or just one makes it kind of the most canonical, but I could have put pi and pi in here. All I need is x2 equals x3, but this has to be 0 for this particular matrix. Okay, so it's not a unique vector that I can choose because I've got all the freedom in my coefficient. Okay, let's do another example and see what that null space looks like. Make it less mysterious. Okay, so it looks really mysterious. Now we see it's a linear combination of some vectors. Let's do A2 equals 1, 0, 0, 2, 1, 0, 3, 2, 1. Nope, I should have changed colors, make things a little more distinct. Maybe I can draw a line here. Okay, so how do we find the null space? We look at solutions of A2x equals 0. So, just taking some simple examples, we're working out all the steps. Then eventually we'll develop powerful tools in Julia where we go ding, and out pops all the vectors whose linear combinations give us the null space. But we're not there yet. We're still in the grind it out, try to get a feel for what's going on. Okay, so this has to equal 0, 0, 0. Okay. But that's if and only if what? So this is one of our beautiful upper triangular matrix, and we would solve it by back substitution. So we get x3 equals 0. Because x3 is 0, we end up with x2 equals 0. Because x2 and x3 are 0, we end up with x1 equals 0. So this is if and only if, because we have this beautiful triangular matrix and we can do back substitution. Okay, if and only if x1, x2, x3 is equal to the 0 vector. Okay, so null of A2 equals the 0 vector in R3. Okay, so, and you don't have to, in no book will you see the 3 times 1 written, okay? You're supposed to know it's the 0 vector in R3, okay? Sometimes you may write it like this, okay? But normally you just write it and you have to know which vector space the 0 is in. Okay, because if you're in R211, you're not going to write out all the zeros, okay? We all agree on that. Good. Okay, so the null spaces, you're just finding solutions of equation A equals 0. Okay, and it could be the only solution to that is the trivial solution, like this. Whoops. Bingo. Could be the trivial solution like this turned out to be, or there could be non-trivial solutions to Ax equals 0, and then you have a non-trivial null space. And that's tied to the non-uniqueness of solutions of your equation. Okay, there we go. Let's find the range of a matrix now. And it'll be similar to the one we just did, but a little bit different. 2, 0, 0, 3, 2, 1. So the range of A is equal to the set of all points that look like A times X, where X is in the domain, and this is a 3 by 3 matrix, so the X is in R3. So all we've done here is write down the definition, and I save myself one symbol because I didn't write it the set of all y such that y equals ax for some x, okay? I just saved myself one symbol. Big deal, okay? So that's the only shortcut I took. I plugged in exactly what the things look like in the range. So now let's plug it in a little bit more. So it's all things that look like 1, 0, 0, 2, 0, 0, 3, 2, 1, times X is in R3. So, okay. And so now I can write that as X1, X2, X3 is an arbitrary vector in R3. So that's the range. Letting you catch up. There's my matrix. Range is all things AX, and I just write that down. Now I'm going to do a little bit like we did in homework, last week's homework on problem 6, where I just kind of had you change coefficients because, we're used to thinking of x as a variable, but this is the same thing as if I write 1, 0, 0, 2, 0, 0, 3, 2, 1. And now I'm going to put in things that we like to think more of as constants, okay? So if we call them A, B, C, or alpha, beta, gamma, they're just a more innate response that we think, oh yeah, those are just the constants that we use when we make linear combinations. And so I'm going to emphasize that by just saying, yeah, each of those components is a real number. I haven't done anything. All I did was change my shirt, okay? I just changed the name of my variables here. I just said instead of calling them x's, I'm going to call them alphas. And I know vectors in R3 just means each of the components are real numbers. I haven't done anything really here except change the symbols, but I hope that makes it more concrete when I do this next step. So what do we do when we take a matrix and we multiply it times a vector? Well, we take the first column of the matrix times the first element of the vector. We take the second column of the matrix times the second element of the vector. And we take the third column of the matrix times the third column of the vector. That's our column times row definition of multiplication. Now the rows here are really simple. They're single elements, but it still works, okay? So this is just alpha 1, 1, 0, 0, plus alpha 2 times 2, 0, 0, plus alpha 3 times 3, 2, 1, such that alpha 1, alpha 2, alpha 3 are real numbers. So, what is another way to think of the range of a matrix? It's the set of all linear combinations of its columns. That's all it is. Because that's what A times X is. It's just a linear combination of the columns of A. We look at A times X and we think equation. Now we're thinking the algebraic geometry underneath the equation. It's really just linear combination of the columns. Okay, so these are vectors. These two vectors are dependent, right? One is 2 times the other. Do I need both of them? No, just throw it away. Okay, so just throw it away. So this is now equal to set of all alpha 1, and I don't know, I could keep the other one, but it's nice to have ones in your vectors. It just seems kind of normalized. And then I'll put alpha 3 here, 3, 2, 1, such that alpha 1 is in the reals and alpha 3 is in the reals. Bingo. That's the range. That's the range of A. Just as a reminder, that's the range. Okay, the range of A is a linear combination of the columns of A. We'll see that's the general thing. We'll write it down. Okay, now I just want to make an observation to motivate a definition. This is linear combinations of some vectors. This is a linear combination of the 0 vector. This was a linear combination of the vector 0, 1, 1. So we're always looking at these things. If we have subspaces, we often see that we're writing them as linear combinations of vectors. And so instead of just writing this out every time, you want a notation that says, if I have a set, I just generate linear combinations from it, done. It's like an operation, okay? So that's what we're going to do. And it just gives us a shorthand, clean way to work with something. So this is the span of a set of vectors is what we're going to define. And how mathematicians were motivated to make this definition is because they found themselves confronted time and again of writing down all the possible linear combinations of a set of vectors. So just give it a notation and move on with your lives instead of plugging up your page with writing that out all the time. So here it is. Whoops. In my disappearing ink, here it is. Let S contained in Rn be a subset. A set of all possible linear combinations of elements of S is called the span of S. Whoops. Okay, I'll write it down like two different ways. One, once again, wordy. One with symbols. We'll see which one you like best. Span of S. It's the set, already got the braces, it means set. All possible linear combinations from S Another way to say it, a vector V is an element of the span of S if and only if one can find some k bigger than or equal to 1, constants alpha 1 to alpha k in the reals, v1 to vk in S, such that v equals alpha 1 v1 plus alpha 2 v2 alpha k vk. Okay, let's catch our breath, catch up with the writing. Okay, so let's go back and just do something concrete. So we had range of A is equal to alpha 1 times 1, 0, 0, plus alpha 3 times 3, 2, 1, alpha 1, alpha 3 in R. Okay, here's the professional way to write that. It's the span 1, 0, 0, 3, 2, 1. Okay? Set of all linear combinations of those two vectors. Let's see, we had null of a matrix I called A1 was the set of all alpha times 0, 1, 1, such that alpha was in the reals. Okay, here's the professional way to write that. Span of 0, 1, 1, okay? So it's just a shorthand for all the set of linear combinations. It's harder to write down than it is to use in most cases. So here's one where we had two vectors in the span. Here's one where we only had one vector that we took linear combinations of. And if I did the one that had the null space of 0, it'd be the span of the 0 vector, which is just the 0 vector. That's fine. So in principle, it takes a lot of work to generate the span because you have to do all possible linear combinations. You have to find k can go 1, 2, 3, 4, 5 up to 67 million and raised to power of Avogadro's number. Then you find all these real numbers. And then you find all these vectors in S, and then you take all these linear combinations. So in principle, it's just a huge thing. Yep?
Why didn't we eliminate alpha to?
In the previous example? Mm-hmm. So this one here. Yep, and it's because, let me like the question, let's do that. So let's look at these two vectors. It's really the vector this gives me alpha 1 plus alpha 2, 0, 0. And then I can write that as an alpha tilde times 1, 0, 0. So when I add those two up, it doesn't give me another direction. That's why I threw away one of them. Is that the question? Mm-hmm. Cool. Yeah, so the reason I threw it away is because I saw 1 that gives me alpha 1 plus alpha 2, and I can just replace that. Or I can just look at this and just keep one of them because this one is a multiple. So it's kind of a short trick. But if you don't like the short trick and you're just learning, yeah, the question is very well posed. Just write this out. This is the vector. That defines a new coefficient, and then let that coefficient vary over all possible real numbers. And that's what's happening here because alpha 1 is over all real numbers. Cool. Okay, so span, we just generate linear combinations, but in practice, it's not a big deal. We're using it as a notational shortcut for instead of writing down all these things. Okay, so that's what the span is, generate a subspace. And in fact, that's a very important note. Okay, so S is just a subset. It is not necessarily closed under linear combinations. So we close it. We take all the possible linear combinations till we get nothing more new. So by definition, the span contains all possible linear combinations, so the span of S is always a subspace. Okay, it's always a subspace. It wasn't an accident. The range is a subspace, we wrote it as a span. The null space is a subspace, we wrote it as a span. The span, because it contains all possible linear combinations, this is closed under linear combinations, because if you take two vectors in here and you add them up, well, that's the same thing as taking more linear combinations over here. So span of S is always a subset. Any set you have, excuse me, it's always a subspace. Okay, and then the span is simply a mechanism to generate a subspace from a given set of vectors. Okay, it's abstract, but yet it's concrete and convenient. Oh, okay. Triby's just following up. See, that's clear or not. Good. Okay, let's do another example. We'll use the vector space R3. And we'll assume S has two vectors in it. 1, 0, 0, 0, 1, 0. Okay? We typically call this E1 and this E2. These are these magical columns of the identity matrix, okay? So is S a subspace? No, because the vector 2, 0, 0 is not in there, okay? It's not closed under linear combination. Does it pass the smell test? No, the 0 vector is not in S. It has two vectors, okay? S is just a subset, okay? It's just a subset. Let's do the span of S. So it's the span then of 1, 0, 0, 0, 1, 0. Then all the mystery is gone as soon as we write this out. It looks like alpha 1 times 1, 0, 0 plus alpha 2 times 0, 1, 0. And alpha 1, alpha 2 are real numbers. Okay, well, let's take it a little bit further. You catch up on your writing. So we just wrote down the definition of the span, all possible linear combinations of the elements in S. There's only two elements, so we only need two coefficients to generate that. Okay. So this looks like alpha 1, alpha 2, 0. Alpha 1, alpha 2, real numbers. Now I'm going to pull the opposite trick on you. And I'm not even using x1, x2, x3. I'm going back to the old x, y, z idea of what R3 is. Okay, so that's every vector that lies in the xy plane in R3. Okay, so that's the xy plane. I don't know, I'm terrible at drawing. Whoops. The arrows always go up. And this one I shouldn't have had there. Yeah, I should do something like this. Y. Ooh, doesn't that look good? That's pretty good for me. So here's X, here's Y, here's Z, and I don't know. I don't know if you can see that's a two-dimensional plane in R3. You probably can't, but that's my best approximation, okay? So it's just the XY plane in R3. That's what that span does. Span of the first unit vector 1, 0, 0, 0, 1, 0. This third component is always 0, okay? So this component is always 0. So it's always the plane, XY plane in R3. So that's what that generates. Okay, so one more cool thing and then we'll be done. Definition, and this is of the column span of a matrix. So let A be an n by m matrix. Okay, so then its columns are vectors in Rn. Okay, so A has 100,000 rows and 27 columns, okay? So we have columns with 100,000 elements in it. That's a challenge, but we can still call it. We can still work with it, okay? And it's literally this, the span of the columns of A is called the column span of A. It's almost Department of Redundancy department, called the column span of A. So I'll write it down slightly differently. Column span of A equals span. These are now vectors in Rn. So here's A1 column. Here's A2 column. Here's AM column. Okay, so that's it. So, but next time we're going to tie up all of these disconnected things. Next time, tie up all of these concepts. Into one united picture of how range, column span, the existence of solutions, all of that stuff ties together, okay? So, thank you. We're at our time limit. Just don't have time to get into bases. That's where we're headed. And cool. I do have a question. So far, we have a grand total of 3 people who have voluntarily started building their Google Doc, okay? 3. There's going to be no homework due this week. I mean, okay, you have the one you're turning in this week, but no homework posted this week for next week. Try to talk me out of making the homework for next week to just make a Google Doc on either the theory or Julia. Tell me why I shouldn't make that a homework.
Is our project open next week? Or
Excuse me?
when does the next project start?
We're going to post the project in 2 weeks. Yeah. I think it's, or is it maybe next Thursday? Maybe next Thursday we post the project. I just put the thing in there. Yeah, we'll post the project next Thursday, and you're going to have 3 weeks to do the project instead of 2, okay? And then about a week after that, we post the last project, and it's due the very last day of class. You'll have 2 weeks and 4 days or something like that for the very last project. We're trying to make sure you got plenty of time. So what do you guys think? I mean, you get to drop your 2 lowest homework, so I guess if you don't want to make this cheat sheet, you don't have to. But I guarantee you it's the only way to integrate all this stuff. So talk me out of it? You want to talk me out of it? No? Talk me out of it? Okay. I guess we're going to go for it then. Got it. Okay. Thank you, guys.